Hello, everyone. Welcome to our podcast, where today we'll be diving deep into the paper titled Optimizing Edge AI, a comprehensive survey on data, model, and system strategies. Are you ready to explore the world of Edge AI with me?
Absolutely. Edge AI is such a hot topic these days, especially with the rise of 5G and the proliferation of edge devices. To start, can you explain what Edge AI actually means?
Of course. Edge AI refers to deploying artificial intelligence algorithms directly on edge devices, such as smartphones, sensors, and IoT devices, instead of relying solely on cloud computing. This allows for local data processing, which reduces latency and improves privacy. Isn't that fascinating?
It really is. The paper mentions that by 2025, about 75% of enterprise-generated data will come from edge devices rather than traditional data centers or the cloud. That's a huge shift. Why is this change happening?
The main drivers are the explosion of data generated by edge devices and the need for real-time processing. Sending all that data to the cloud for analysis is inefficient and can cause delays. Edge AI enables faster responses and helps address privacy concerns by keeping data local. Have you seen any real-world examples of this?
Yes, actually. In smart factories, industrial robots use Edge AI to process sensor data in real time, which helps them detect risks and respond quickly. This is crucial for Industry 4.0, where automation and intelligence are key. But deploying AI models on resource-constrained edge devices must be challenging, right?
Exactly. That's one of the core issues the paper addresses. State-of-the-art AI models, like GPT-3, are massive and require huge amounts of storage and computational power. Edge devices, on the other hand, have limited resources. So, the paper proposes an optimization triad to tackle this: data optimization, model optimization, and system optimization. Shall we break down each part?
Let's do it. Starting with data optimization, what does that involve?
Data optimization focuses on improving the quality and suitability of data for edge deployment. This includes data cleaning, feature compression, and data augmentation. For example, data cleaning removes noisy or incorrect data, which is especially important when dealing with sensor data from IoT devices. Have you come across any interesting data cleaning techniques?
Yes, the paper mentions active label cleaning, which identifies and prioritizes mislabeled samples for correction. There's also federated data cleaning, which allows for collaborative cleaning across devices while preserving privacy. But these methods can be resource-intensive. What about feature compression?
Feature compression reduces the dimensionality of data, making it easier for edge devices to process. Techniques like feature selection and feature extraction help retain only the most relevant information. This not only improves model accuracy, but also reduces computational and memory requirements. Can you give an example of where this is used?
Sure. In healthcare, feature selection is used to identify the most important signals from wearable devices for disease detection. This makes it possible to run complex models on devices with limited resources. And data augmentation?
Data augmentation increases the size of training datasets by generating new samples through modifications like rotation, scaling, or adding noise. This is especially useful when data is scarce, which is often the case on edge devices. However, it's important to choose augmentation techniques carefully to avoid introducing bias. Shall we move on to model optimization?
Yes, please. Model optimization seems crucial for running AI on edge devices. What are the main strategies here?
There are two main approaches: model design and model compression. Model design involves creating lightweight architectures, such as mobile nets or SqueezeNet, which are specifically built for efficiency. Neural architecture search NAS is also used to automatically find optimal architectures. Have you heard of any lightweight models?
Definitely. MobileNet, ShuffleNet, and EfficientNet are all popular lightweight models. They use techniques like depthwise separable convolutions to reduce computation. But even these models can sometimes be too large, so model compression comes into play. What does that entail?
Model compression includes techniques like pruning, parameter sharing, quantization, knowledge distillation, and low-rank factorization. Pruning removes unnecessary parameters, quantization reduces the precision of weights, and knowledge distillation transfers knowledge from a large model to a smaller one. Each method has its trade-offs between efficiency and accuracy. Can you elaborate on pruning?
Sure, pruning can be structured, where entire layers or channels are removed, or unstructured, where individual weights are set to zero. Dynamic pruning even adjusts the model during training. The goal is to maintain accuracy while reducing size and computation. But sometimes, pruning can hurt model interpretability or compatibility with certain hardware.
That's a good point. Parameter sharing, on the other hand, allows multiple layers to use the same weights, further reducing the model size. Quantization is also popular, especially for hardware acceleration, as it allows models to use lower precision arithmetic. But if you quantize too aggressively, you might lose accuracy.
And knowledge distillation is fascinating because it lets a small student model learn from a large teacher model, often achieving similar performance with much less complexity. This is especially useful for deploying models on edge devices. What about low-rank factorization?
Low-rank factorization approximates large weight matrices with smaller ones, reducing both memory and computation. It's a powerful technique but can require significant retraining to maintain accuracy. Now, let's talk about system optimization. What does that involve?
System optimization covers both software and hardware strategies to accelerate model training and inference on edge devices. On the software side, there are lightweight frameworks like TensorFlow Lite and PyTorch Mobile, which are optimized for mobile and embedded platforms. These frameworks help deploy and run models efficiently on edge devices.
Exactly. For inference, frameworks like NCNN, OpenVINO, and ONNX Runtime provide optimized implementations for various hardware. They support different platforms and help reduce latency and energy consumption. On the hardware side, what accelerators are commonly used?
CPUs, GPUs, FPGAs, ASICs, and NPUs are all used to accelerate AI workloads on edge devices. Each has its strengths and weaknesses. For example, GPUs offer high parallelism but consume more power, while ASICs are highly optimized for specific tasks but are expensive to develop. FPGAs offer flexibility and low power consumption but can be complex to program.
That's right. The paper also discusses hardware-software co-design, where both the model and the hardware are optimized together for maximum efficiency. This is becoming increasingly important as edge AI applications grow more complex. Speaking of applications, what are some real-world scenarios where edge AI is making an impact?
There are so many. In smart homes, edge AI enables real-time activity recognition and energy management. In industrial automation, it helps optimize production lines and perform predictive maintenance. Healthcare benefits from faster and more accurate diagnostics, while autonomous vehicles rely on edge AI for real-time perception and decision-making.
Public safety is another area, with edge AI enabling real-time video analytics for surveillance and anomaly detection. Agriculture uses edge AI for crop monitoring and pest management, and retail leverages it for inventory management and customer analytics. Energy management and logistics also see significant improvements from edge AI deployment.
With all these benefits, there must be challenges as well. What are the main obstacles to deploying AI on edge devices?
The paper identifies several challenges: limited computing power, limited memory, power consumption, limited communication bandwidth, security and privacy concerns, and model management and scheduling. Each of these requires specific strategies to overcome. For example, lightweight models and hardware accelerators help address computing and memory constraints.
Energy-efficient algorithms and hardware are crucial for battery-powered devices. Communication bandwidth can be optimized through data preprocessing and edge caching. Security and privacy are addressed with techniques like federated learning and trusted execution environments. Model management involves efficient placement, migration, and scaling of models across devices.
Exactly. The paper also highlights future trends in edge AI, such as increased intelligence, flexibility, security, collaboration, and efficiency. As AI chips and edge computing capabilities improve, we can expect more sophisticated and personalized services at the edge.
Collaboration between edge devices and the cloud will also become more important, enabling more complex tasks and better resource utilization. Security will be enhanced through technologies like blockchain, and efficiency will continue to improve with better algorithms and hardware.
In summary, the paper provides a comprehensive overview of the strategies for optimizing edge AI across data, model, and system levels. It highlights the challenges and solutions for deploying AI on resource-constrained devices and explores a wide range of applications and future trends.
That was a fantastic discussion. I feel like I have a much deeper understanding of edge AI and the optimization triad. Thank you for guiding us through this comprehensive survey.
Thank you. And to our listeners, we hope you enjoyed this deep dive into edge AI optimization. Stay tuned for more paper reviews and discussions on the latest in AI research. Until next time.
Goodbye.